Okay, for this set of experiments and a set of demonstrations, we're going to look at some fun and games you can have with dry ice. So solid carbon dioxide. Sublimation point -78 degrees. Now this is not common in secondary schools, but it can be ordered in on special occasions. Here we have some pellets of dry ice and pellets of CO2. Some schools have what they call a snowpack machine that will produce dry snow off one of their carbon dioxide cylinders. It is also possible to order in slabs of dry ice. They look like bricks that you can get through your usual gas suppliers. We just thought we'd show you a couple of experiments with dry ice. Now when you're handling bulk quantities of dry ice, you do need insulated gloves. However, you can actually pick these things up as long as you don't keep them in the same contact with the same piece of skin for any length of time. You can actually pick them up quite safely. A couple of simple experiments we'll look at. We'll put some dry ice into a beaker. We will add in some water. So you can see the classic mad professor experiment where they have it in the films where they're apparently drinking the stuff. I don't recommend drinking. I don't recommend actually putting washing up liquid in that either, because what you'll end up producing is a whole pile of bubbles that just won't want to stop. But it is good fun to see carbon dioxide filled bubbles. Of course, being denser than air, they're going to sink down as well. We'll just get that one out of the way before it fills up this lecture theatre. Carbon dioxide is one of the few solids that sublimes. So sublimation is when a solid becomes a gas without going through the liquid stage. So here I have some latex rubber gloves. Of course, you've got to check with your own students whether they've got any latex allergies. And nitrile gloves don't work as well with this experiment. So I just put in a few grams of dry ice into the fingers. And I'm going to transfer some heat energy from my hands into the dry ice. So I'm touching it for less than a second at a time to transfer some energy. And in doing so, you can see that some of the carbon dioxide is producing carbon dioxide gas. So we've got sublimation going on. We've still got solid in the bottom. And we've got gas being produced. Well, I believe that carbon dioxide goes from solid to a gas by a factor of about 440. So that glove will just get bigger and bigger and bigger, and eventually it will burst. We'll put this to one side. Another experiment you can show that carbon dioxide going from a solid to a gas requires energy is a very straightforward and simple exercise. You can simply take a board and put some water on a board and place a clean beaker on top, and we can add some dry ice to that beaker. Of course, what will happen in order for the carbon dioxide to go from the solid state to the gaseous state, there's got to be some bond breaking. Bond breaking requires energy, and that energy is either going to come from the glassware, the air above it, or the water below the beaker. And we'll leave that for a few moments while we get some more carbon dioxide. Carbon dioxide, by the way, is cold enough that when you blow over it, it's cold enough to condense the water vapor in your breath into tiny droplets of liquid water that you're seeing as cloud. Now we need to wait on this for a moment or two. But we've already got there. We've now frozen the beaker to the board because of the heat energy being removed from the liquid water, making it solid water, freezing it and sticking it to the board. And if we add a bit of force, we can probably see some of the ice forming on the bottom. The last experiment I'm going to show you is straightforward. If you happen to have dry ice pellets rather than dry ice snow. And what we're going to look at is the acidic properties of carbon dioxide. And the reason the pellets work well here and the snow doesn't, the snow is so loose, packed, it's not dense enough to sink into the water or strictly into the alkaline solution. So we've got some water present there, some tap water. We'll add a bit of universal indicator solution. Very difficult to see colour changes against a dark background. So I'll just sit this onto a white board, and if necessary, we'll even put a white board behind it. I want to make the water solution with a universal indicator alkali, so a drop of sodium hydroxide, not too much. If you put a load in, the experiment takes too long. If you only put a small amount in, it goes far too quickly. So there we have a pH of about 11 to 14. What I'm going to do is to drop in a handful of dry ice and look at the colour changes. See a lot of cloud formation because of the water vapour being cooled. And the problem that you can have with this is that you can't see too easily through the cloud. But you should have seen the colour change. Hopefully you'll have seen the colour change going from purple to blue to green to yellow. That yellow will now turn orange. Carbon dioxide solids in that beaker are doing both chemistry and physics. The physics is simply the change of state. The carbon dioxide solid is taking energy away from the water, removing energy from the water, actually cools some of the water down. The carbon dioxide then breaks apart the intermolecular bonds in the solid state and becomes gaseous, a physical chemistry change. The carbon dioxide lowering the temperature produces condensed water vapour from the water vapour that was above it. So we're going from the gas, the water vapour itself, condensing to tiny droplets of liquid as cloud. The chemistry, of course, has gone on in the beaker. We have an alkaline solution that some of the carbon dioxide neutralises, hence the drop through the pH numbers down from 11 to 14, down through 7, through the blue and green. The surplus carbon dioxide stays in the solution as carbonic acid, and carbonic acid is a weak acid, and that's why its pH shows an orangey yellow colour rather than the red coloration of a strong acid.